So what we're going to do now is take a function f of x equals x squared plus 2x squared minus x minus 2. And what we're going to do is we're going to graph this using what we know about functions and their derivatives and such. So first we'll take the function, and this gives us our function values. And then what we can do is you can find the first derivative, 3x squared plus 4x minus 1. This is our slope derivative function. And then the second derivative, it's 6x plus 4. And this tells us about concavity. So, you know from our pre-calculus classes that this function roughly is going to look like this. The leading term has a positive coefficient and an odd degree, so that's the general shape the graph will take on. And we know here we've got a y-intercept of -2. If we factor this function, we get 3 factors: x minus 1, x plus 1, x minus 2. Excuse me, x minus 1, x plus 1, x plus 2. So we have zeros at -2, at -1, and at +1. So there we've got some basic information. We've got our intercepts, both x and y. Now with the first derivative, we can find critical values, which could be potential relative extrema. So if we set the first derivative equal to 0, that occurs where x equals roughly 0.215 and -1.548. And the associated function values are -2.1 and f of -1.548 is roughly 0.6. So setting the finding the critical values where the derivative function equals 0. We got x values of 2.215 and -1.548. And if we find the associated function values, we have points which are potential relative maxima, relative minima. So let's graph those. 0.21, -2.1. And when the x is -1.548, we have a function value roughly 0.6. Alright, so now we've got some points on the graph. We can also find where the first derivative is less than 0 and where it's greater than 0. This would tell us intervals on which the graph is increasing. So looking at critical values of -1.5 to 0.2. Oops. 5 and 2 using the sign test. So let's take a x equals 3, negative 3. And the derivative of that point is 14. And so in this interval from negative infinity to negative 1.5, first derivative is greater than 0, which means the slope is positive, which means the function is increasing. So here we have the turning point, slope of 0. And then if we look at this interval here using the sign test, we get, say we use a test point of x equals 0, the derivative, first derivative equals negative 1. So slopes are negative, which means the function is decreasing. So extrema, and then taking the value of x equals 2, plugging that into the first derivative, we get 19, which is positive. So slopes are positive, function increasing. There's our rough sketch of the graph. Now what we can do is, at these relative maxima or minima, or at those values, if we find second derivative is positive, we have concave up, which means the relative extrema would be a minimum, and if the second derivative is less than 0, we have concave down, which would mean the point is a relative minimum, or maximum, sorry, concave down, relative maximum. And when we find second derivative set equal to 0, we can find inflection points. At this point, negative 1.5, plug that into the second derivative, you get 6 times negative 1.5, which is 9, plus 4 is negative 5, so that's negative. So in fact, this is concave down, it's a relative maximum, and at the point 0.2, 6 times 0.2 is 1.2, plus 4, 5.2, that's positive. Concave up in this section. The second derivative equals 0. So it equals 0 when x equals, so when 6x plus 4 equals 0, or when x equals negative 2/3. So roughly right there is our inflection point. We go from concave down to concave up. And there's our not so pretty, but pretty graph of a function.